In this lecture, we will look at some of the main properties of context-free languages. If L1 and L2 are context-free languages, then also the union of L1 and L2 is a context-free language, the concatenation of L1 and L2 is a context-free language, the Kleene star of L1 is a context-free language, and the reversal of L1 is context-free. So the class of context-free languages is closed under union, concatenation, Kleene star, and reversal. Let's prove this. If a language is context-free, then we have context-free grammars for the language. So let G1 be a context-free grammar for L1 with starting variable S1. Let G2 be a grammar for L2 with starting variable S2. And without loss of generality, we may assume that our grammars G1 and G2 have no variables in common. If they have variables in common, then we simply rename the variables of one of the grammars. Now, how do we get a grammar for the union of L1 and L2? So we want to make a grammar that can generate any word from L1, but also any word from L2. The basic idea is that we take the union of the two grammars G1 and G2, but we need some fresh starting variable and we need also new rules. Namely, we take the union of the two grammars and we add two rules. We have a fresh starting variable S, and we say that S can rewrite to S1 and S can rewrite to S2. Recall that S1 is the starting variable of G1, S2 is the starting variable of G2, so by saying that our fresh starting variable can rewrite to S1, it means we can generate any word from the language L1, and since S can also rewrite to S2, we can also generate any word from the language L2. So this grammar generates the union of the two languages. So similarly, if we want the concatenation of L1 and L2, we also take the union of the grammars. We also add a fresh starting variable S. We add a slightly different rule, namely we add the following rule. We say that S can rewrite to S1, S2. So what does this help? This makes sure that this first part will generate a word from L1 and S2 will generate a word from L2. So from S we can generate all words of which the first part is from L1, the second part is from L2, so we generate all words in the concatenation L1, L2. What about the Kleene star of L1? Now we take our grammar G1, we add a fresh starting variable and we add fresh rules. Namely, we add fresh rules as follows. We say that S can rewrite to S1 S or to lambda. So S can generate the empty word, or it generates S1 followed by S, so it can generate an arbitrary word of the form S1, 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 S1. So it can generate arbitrary number of S1s, and from each occurrence of S1 we can generate a word from L1, and that's exactly what we want. The Kleene star of L1, this is all the words that you can construct from the building blocks in L1, so all the words that you can construct by concatenating words from L1. By generating an arbitrary number of S1s, we can use an arbitrary number of building blocks from the language L1. Now what do we do with the reverse of L1? The idea is that we modify the rules of our grammar. We reverse the rules, so for every rule xy, we change the rule into reverse of x to reverse of y. So this reversal works in general for all grammars. If you have a grammar for a certain language, if you reverse the left and the right hand side of all the rules, then you get a grammar for the reverse of the language. Now, since we are talking here about context-free grammars, actually the reversal of the left-hand side is not needed because the left-hand side is a single variable. If you reverse a single variable, you just get the variable itself. The class of context-free languages is not closed under intersection. So there are context-free languages L1 and L2 for which the intersection L1 with L2 is not context-free. So for instance, take these two context-free languages. So L1 is a language consisting of words of the form a to the n, b to the n, c to the m, where n and m are natural numbers. So we have words that start with a number of a's, followed by a number of b's, followed by a number of c's, such that they contain the same number of a's and b's. And it's not difficult to give a context-free grammar for this language. We just have to make sure we generate the same number of a's and b's and an arbitrary number of c's in the end. L2 is a language consisting of words of the form a to the n, b to the m, c to the m, where n and m are natural numbers. So it's similar words starting with a number of a's, then a number of b's, then a number of c's, but this time we require that we have the same number of b's and c's. And similarly, it's not difficult to give a context-free grammar for this language. We just make sure that we have the same number of b's and c's and an arbitrary number of a's in the front. Now both of these languages are context-free, but if we take the intersection of the two languages, then we get a language that we already know, namely the language consisting of words a to the n, b to the n, c to the n, and we already have proven that this language is not context-free. So why do we get this intersection? We have here the same number of a's and b's, and in the language L2 we have the same number of b's and c's. If we intersect, then we get all words where we have the same number of a's as well as b's as well as c's. So the intersection of context-free languages is not necessarily context-free. And because of this, we may also conclude that the complement of a context-free language is not always context-free. And also the difference of context-free languages is not always context-free. How can we conclude that? The intersection of two languages, L1 and L2, can be expressed as follows. The intersection of L1 and L2 is equal to the complement of the union of the complements of L1 and L2. So the intersection can be expressed by union and complement. We have already proven that the union preserves context-freeness. So the union of context-free languages is context-free. If the complement would preserve context-freeness, then the intersection would also. But we know the intersection does not, therefore the fault must lay with the complement. The complement does not preserve context-freeness. Likewise, we can express the complement by a difference, namely the difference of the language consisting of all the words over a certain alphabet minus the language L1. So the complement of L1 is sigma star minus L1. If the difference would preserve context-freeness, both languages sigma star is context-free and L1 are context-free. If the difference would preserve context-freeness, then the complement would always be context-free. But we've just argued that the complement is not always context-free, therefore the fault must lay with the difference. The difference can also not be always context-free. So the class of context-free languages is not closed under intersection, it is not closed under complement, and it is also not closed under difference. So we have seen that the intersection of context-free languages is not necessarily context-free. However, if one of the languages is regular, then the intersection is again context-free. So if L1 is a context-free language and L2 is a regular language, then the intersection of L1 with L2 is context-free. The proof is basically the product construction that we've seen before. So let's assume that we have a non-deterministic pushdown automaton M for our language L1, and we have a deterministic finite automaton N for our regular language L2. Then we do the product construction, so we construct an automaton, an NPDA M hat, whose set of states is the product of the set of states of our two automata. So the product of the set of states Q of our NPDA and the set of states R of our DFA. The starting state of the new automaton is the pair of starting states of our NPDA and our DFA. And the final states is the product of the final states of the NPDA and the final states of our DFA. So we accept if the NPDA as well as the DFA accept. So now how do the transitions of our new NPDA work? Basically, the transitions model the transitions of our original NPDA M. So M hat does basically the same transitions as M if we forget about the second entry of the pair here. So if you forget about R and R prime, then you have precisely the transition of our original NPDA M. Namely, we switch from Q to Q prime if we read input symbol A and we have a B on the stack, and we remove the B and replace it by V. And our NPDA M hat does the same thing. It switches from Q to Q prime, reading an A from the input if there's a B on the stack, and then the stack symbol B is replaced by the word V. Now additionally, M hat simulates what our DFA N does. Namely, if we are in state R of the DFA and we read input letter A, then we check where does the DFA switch to, let's say R prime, then our NPDA M hat also switches to R prime. So in short, M hat does the same as our NPDA M, but in the second entry of the pair, it simulates the DFA. And if we have a lambda transition in our original NPDA M, then we just do the same lambda transition in M hat. And since there is no input for this lambda transition, the DFA just stays in the same state. So for a lambda transition, the DFA does not change the state. So our NPDA M hat behaves like our NPDA M, and in the second entry of the pair simulates the DFA, and we accept if and only if both the left entry of the pair, which simulates the NPDA, as well as the right entry of the pair, which simulates the DFA, if both accept, therefore the language of the NPDA M hat is the intersection of the languages of the NPDA M and the DFA N. So why does this construction that we've just seen not work for two NPDAs instead of an NPDA and a DFA? So we have seen that we can do the product construction for an NPDA and a DFA. So what goes wrong if both M and N are NPDAs? The problem is that then we have two automata with a stack, and we cannot simulate two stacks at the same time. If the second automaton is a DFA, then we just simulate the change of the state, but we do not have to simulate the stack for the DFA. So the product construction does not work because in order to simulate two automata with two stacks, we would need an automaton with two stacks, but an NPDA has only one stack. The difference of a context-free language minus a regular language is again context-free. So if L1 is a context-free language and L2 is a regular language, then L1 minus L2 is again context-free. And here the order is very important, because L2 minus L1 is not always context-free. We already know that the complement does not preserve context-freeness. But the complement can be expressed by sigma star minus L1. Sigma star is a regular language, so if L1 is a context-free language, then this is not always context-free. So a regular language minus a context-free language is not always context-free. But the other way around, it is. A context-free language minus a regular language is always context-free. And the proof is quite simple, namely the difference of L1 minus L2 can be expressed using intersection and complement. It is L1 intersected with the complement of L2. If L2 is a regular language, then the complement is regular again, and we already know that the intersection of a context-free language and a regular language is context-free. So here it's important that L2 is a regular language in order to conclude that the complement is again regular. We can use the theorem that we've just seen to prove that certain languages must be context-free. For instance, if we have a context-free language and we remove a finite language from it, so for instance here just the empty word, finite languages are always regular, so the result must be again a context-free language. Likewise, in this case, we already know that a to the n, b to the n for n greater equals 0 is context-free. If we now restrict n to be greater equal than 1000, then we know that this is basically the same language, but we've dropped finitely many words, namely 1000 words from the language. We have removed finitely many words, that's a regular language, so the result must be context-free again. This theorem can also be helpful for proofs that certain languages are not context-free. So for instance, assume that we want to show that this language is not context-free. That's the language of all words W over ABC that contain the same number of A's as B's as C's. Now, for contradiction, assume that this language L would be context-free. If this language was context-free, then it's also context-free if we take an intersection with a regular language. So let's intersect this language L with the language of the regular expression A star, B star, C star. So let's say that we take all the words from L that start with a number of A's, followed by a number of B's, followed by a number of C's. So if we have words of this form, and these words have the same number of A's as the number of B's as the number of C's, then we have words of the form A to the n, B to the n, C to the n for n greater equals 0. So the intersection of L with the language of this regular expression is a language that we already know, and we have already proven that this language is not context-free. So since the intersection of L with a regular language is not context-free, it follows that our assumption must have been wrong. L was not context-free. Now let's have a look at properties of context-free languages and whether these properties are decidable, so whether we can write a program that tells us whether the property holds or not. Given two context-free grammars, G and H, the following questions are quite natural and we would like to know whether they are decidable. So for instance, given an input word W, can we decide whether W is in the language of the grammar? Can we decide whether the language generated by a grammar is empty? Or whether the language generated by a grammar contains all words of the alphabet? Can we decide whether the language generated by a grammar contains a palindrome, so whether the grammar generates a palindrome? if you have given two grammars G and H, it's natural to ask whether these grammars generate the same language. So are these grammars equivalent? And it's natural to ask, do they have any words in common? So is the intersection of the language generated by G and the language generated by the grammar H, is the intersection empty? So all these are quite natural questions about context-free grammars, and we would like to have answers to all of them, but somewhat surprisingly, only the first two questions are decidable. So for the first two questions, we can write a program that answers these questions. For all other questions, it is impossible to write a program that always answers these questions correctly. We cannot decide whether a grammar generates all words over the alphabet. We cannot decide whether two given grammars are equivalent. And we cannot decide whether two given grammars have a non-empty intersection of the languages. So only the membership and the emptiness are decidable. And the decision procedure is quite simple. We take our grammar G, we remove lambda and unit productions, and once we have removed lambda and unit productions, we can compute all the words that are derivable from the starting variable up to the length of our input word W. So this is a finite set, and since there are no lambda productions, the words that we derive never get shorter. So we only have to consider a finite number of words that we derive, namely up to the length of W. And then we can compute this finite set, and we can simply check whether W is among these words or not. It is decidable whether the language generated by a grammar is empty. Namely, we have already discussed how we can check whether a variable is useless, and the language generated by a grammar is empty if and only if the starting variable is useless. So if and only if the starting variable can never be used in a derivation of a terminal word. So the first two problems are decidable, all other problems are undecidable. And we are going to prove this formally by using Turing machines. We will show that there are certain undecidable problems for Turing machines, and then we will show that this implies that also these questions about context-free grammars are undecidable.